All right, so here's another ugly looking integral. This one almost looks like you could do substitution on it, but if you if you were to let w equal x squared plus 2x plus 5, then you'd end up with 2x plus 2. It just doesn't quite match the top. So this one we're going to try to complete the square again on it. So let's complete the square. We've got x squared plus 2x, okay? And then we want to add something to it to make it a perfect square. And then of course we have the plus 5. Okay, so this is the same thing that we have in the denominator here, but we want to complete the square. I'm going to take half of this middle coefficient and square it. So I get 1. Now I just added 1, so to balance it out, I've got to subtract 1. So I haven't really changed anything, right? I've added 1, I've subtracted 1, so I basically added 0. But when I do that, then this thing in parentheses becomes x plus 1 squared. And then, of course, 5 minus 1 is 4. Okay, so I can rewrite this integral as x over x plus 1 squared plus 4 dx. All right, so now this looks more like something we've seen before. We've got something squared plus a constant, which says to me, let's try a tangent substitution. All right, so I'm going to say, let's let x plus 1 be, and I have 4 over here, so I'd like to have a 4 when I square the x plus 1. So I'm going to make x plus 1 equal 2 tangent of theta. All right, and if I differentiate both sides, then I get dx is equal to 2 secant squared theta d theta. All right, now let's just put that all together in here and see what we got. So I'm going to rewrite this integral. Now the top is x, right? So x is 2 tangent theta minus 1, right? Because I assigned 2 tangent theta to x plus 1. So now I need x. So I get 2 tangent theta minus 1. And then in the bottom, I'm going to get 4 tangent squared theta plus 4. Okay. And then I have to multiply that times the dx, which is 2 secant squared theta d theta. All right. That looks kind of ugly, but I know if I factor out, if I factored the 4 out of the bottom here, so let's just write the denominator down here first. I get 4, and then I'm going to have tangent squared theta plus 1, okay, and that's all over, or that's under 2 tangent theta minus 1, and then I have 2 secant squared theta d theta. All right, and I know that this tangent squared plus 1 becomes secant squared, right? So, I could just cancel this straight out and not write another step. And then you can see we can cancel. We've got a 4 in the bottom here, right? So I can make this into a 2. Now be careful, because this 2 in the numerator is only times tangent. It's not 2 times the whole quantity tangent. So I can't cancel that 2 yet. So be careful. I found myself trying to do that as I was doing this problem. So let's rewrite this and make it look better. So I'm going to have, I'm just going to bring this out front. 1/2 integral of basically 2 tangent theta minus 1 d theta. Okay? All right. So I can split that up into integral of, because it's basically the sum of 2 tangent theta plus a negative 1. So I can split that up, and so that becomes, okay, so I'm going to have 1/2 integral of 2 tangent theta d theta, and then minus 1/2, so I'm just distributing the 1/2, all right, integral of 1 d theta. Okay, so this one's easy. I'm just going to write this off to the side. So we get minus 1/2 theta plus c. All right, I'm just going to write that off to the side. This other one's a little trickier. All right, so we have to integrate tangent. So I can actually cancel out now the 1/2 times the 2 just becomes 1. So now I have to integrate tangent of theta d theta. And in order to do that, I am going to write it as sine theta over cosine theta, because then it becomes a little more obvious that I can do a substitution, right? So I could let w equal cosine of theta, so then dw is equal to minus sine theta d theta. All right, so that means that minus dw is equal to sine theta d theta. And you can see the sine theta d theta is right there in the numerator. So when I do that, I'm going to get, so let me write that down here, I guess. We have minus integral of 1 over u, or w. I guess I wrote w. W dw. All right, and that's just the natural log. So I get the minus natural log of the absolute value of w plus c. Okay, and then I know what w is. I can substitute w, so I get minus the natural log of the cosine of theta plus c. All right. All right, so if I put that all together, I have this natural log term, and then I also have the theta term, right? Because I have to go back to my original integral that I was trying to solve. So I just had to do this little tangent integral off to the side. So let's see. If we put it all together now, I'm going to have, well, let me just write it here. I'm going to have minus natural log of cosine of theta minus 1/2 theta plus c. All right, that's what, if I go back up here, that's what that becomes. This was just all kind of a side calculation here. All right, so but now I have to go back to x. So I can go back up to my substitution, and I know that theta has to be equal to the arctangent of x plus 1 over 2. Okay, so I can do the theta, but in order to get the cosine, I probably have to draw the triangle. So let me draw the triangle off to the side here. So I'm going to draw my little triangle. This is theta. And I know that tangent of theta is going to be x plus 1 over 2. Okay. So then if I combine those, if I use the Pythagorean theorem, I'm going to get x squared plus 1 squared plus 2. If I combine that, again, I end up with x squared plus 2x plus 5. So that's my hypotenuse. And then the cosine is just going to be 2 over the square root of x squared plus 2x plus 5. All right, so this is going to look pretty ugly. So we get minus natural log of, all right, so it's a positive square root, right, and then it's positive, so I really don't need those absolute value signs anymore. So 2 over the square root of x squared plus 2x plus 5. Yeesh. Minus 1/2 times the arctangent of x plus 1 over 2 and plus c. All right, I know that's not pretty, and there's probably some things I can do to clean this up because I have the log of a quotient, and then I have the square roots. I could there's probably some ways I can clean this up a little bit and make it look prettier, but I don't really have any reason to, so I'm just going to leave that as it is and call this my final answer. And so that's it. That was a little more complicated, but yeah, it's doable, right? So, all right. Next thing is just discussion questions. I guess I do have one other. I've got a little bit of a summary here. Now, you know, if you practice enough and as you get the hang of it, you probably won't need to look at this summary. You'll be able to see that if you've got something with, you know, a constant minus nx squared, we can use the a substitution of sign. And if we have a constant plus nx squared, then we can use a tangent substitution. And it'll make sense. So I don't know if you need this. Here's the triangles, you know, for the different types of substitutions. So, but it's there if you want it initially for reference. But if you just think it through, you probably won't need this this summary. So try the discussion questions, and we'll see you in class.